In today's video, we're going to take a look at standard H2 electric fields. We've talked about Coulomb's law, we've talked about charging, and we've talked about methods of charging. Now we want to take a look at how electric fields develop around charges. And we say that an electric field is a property of space near a charge, so that the mere presence of the charge affects the space around it. It has a field around it, and that means that if we place a charge near that first charge, the electric field itself will help us determine how that second charge placed there will respond to the first. Electric field strength is a vector value, and its direction is that which a positive charge would experience. So when we identify the vector diagrams themselves, we're always going to point the arrow in the positive direction, or how a positive charge would move in the field itself. The symbol for electric field is the capital E, and the units for electric field are newtons per coulomb. The equation for electric field is the electrostatic force felt by a charge at some position divided by the magnitude of its charge itself. Because electrostatic field strength is K Q1 Q2 divided by R squared, we could actually simplify this electric field equation, so we don't have to figure out what the electrostatic force is, and just take the electrostatic constant multiplied by the charge itself divided by the distance from that charge that we're interested in. So we have KQ divided by R squared will tell us the electrostatic force that's felt at some distance away from a charge. All we need to know is the magnitude of the charge itself and how far away from the charge we're looking at. Electrostatic or electric field strength follows the inverse square law, very similar to how the electrostatic force does. They both follow that same relationship. So let's go ahead and try an example of this. And I want to know, what is the strength of an electric field midway between a 2 microcoulomb charge and a 4 microcoulomb charge if they're separated by 0.6 meters each other? My strategy for this problem is this. I want to figure out at the point midway, I'm going to determine what the electric strength from one is and what the electric strength from the other one is. And because they're vectors, I'm going to add them together. I have a 2 microcoulomb charge and a negative 4 microcoulomb charge. So one of the charges is going to be pushing and one is going to be pulling. Once I find the magnitude of their two electric field strengths, I'll add them together like vectors. So let's go ahead and find the electric field strength from the first one. In this one, we have the 2 microcoulomb charge multiplied by the electrostatic constant. And if it's midway between them and there's 0.6 meters apart, that means that this is 0.3 meters away. So the first one is giving me 2.0 times 10 to the 5 newtons per coulomb. This is repelling it, or a positive charge would be repelled by it. So the field strength is pointing away from the first charge. Second charge is a 4.0 times 10 to the negative 6 coulombs. That's a negative charge. I determined this one to be 4.0 times 10 to the 5 newtons per coulomb, but this one is attracted. So the first charge is pushing away at the midpoint, and the second charge is pulling at that, but those are going in the same direction, right? So in between the two charges, one is pulling and one is pushing, but they're both ultimately contributing the effect of the electric field in the same direction. So the two of them actually are added together. You have to be very careful when you're doing electric fields or any electrostatic force that you don't take any credence into the signs themselves. You have to orient yourself spatially. One of these would come out positive, one of them would come out negative, so you have one repelled, one attracted. But looking at them, since you're looking at the spot that's directly between them, adding their vectors together instead of subtracting them, even though they came out with different signs. So whenever you're dealing with electric fields or electric forces, you always want to just take the magnitudes, then orient yourself afterwards. So let's add these two together. So we have our total electric field is the electric field from 1 plus the electric field from 2, and that gives us 2 plus 4, or 6 times 10 to the negative 5 newtons per coulomb.